In this video, I want to explain why this property is true for when the variables are real and all expressions to calculate the values on the left and right hand side are real. Here's my outline so that you can know what I'm talking about and in what order. So first I'm going to explain this property for the case of positive integer exponents or counting number exponents, negative integer exponents, and then zero exponents, as zero is neither positive nor negative, rational exponents or exponents that can be written as a fraction, and then irrational exponents. Let's talk about positive integer exponents. For example, 2/5 and that cubed. Well, that would be 2/5 times 2/5 times 2/5 based on the definition of exponents, repeating multiplication. Now 2/5 is equal to 2 times 1/5. And now for multiplication, it does not matter which order you use. And now based on the definition of exponents, 2 times 2 times 2 is equal to 2 cubed. Also, based on how you multiply fractions, which is you multiply both the numerators and denominators, 1/5 times 1/5 times 1/5 would be equal to 1 times 1 times 1 over 5 times 5 times 5, which would be 1 cubed over 5 cubed, which is equal to 1 over 5 cubed. And then you get 2 cubed over 5 cubed. And you can do likewise with variables. What about when you have negative integer exponents? For example, 2/5 and that to the negative 3. Now based on a property that I plan to explain later in this set of videos about negative exponents, that will be equal to 5/2 and that cubed. Now we already know that this property that I'm trying to prove in this video, that is a power of a quotient, that works for when you have positive integer exponents. And so this will be equal to this. And now again, we use that property that we're trying to explain later in the set of videos about negative exponents, and we get this. And you can do likewise with variables. What about when you have a zero exponent? For example, 2/5 and that to the 0 power. Now as I explained later in the set of videos, anything but 0 and that to the 0 power is equal to 1. And now 1 is equal to 1 over 1. And again, we use the idea that anything but 0 and that to the 0 power is equal to 1. And you can do likewise with variables. 2/5 and that to the 2/3 and that cubed. Now based on the property of the exponents that I plan to explain later in this set of videos, a power of a power is equal to a power times a power. Now 2/3 times 3 is equal to 2. And now we use the property that we're trying to show why it works in this video, as we already shown that it works for when you have integer exponents and 2 is an integer. And we get this. Now 2 is equal to 2/3 times 3. And now a power times a power is equal to a power of a power. And again, we can use this property that we're trying to show why it works in this video, as we already shown that it works for when you have integer exponents and 3 is an integer. And so we get that 2/5 and that to the 2/3 and that cubed is equal to parentheses 2 to the 2/3 over 5 to the 2/3 and that cubed. And so 2/5 to the 2/3 is equal to 2 to the 2/3 over 5 to the 2/3. And you could do likewise with variables. However, the last step you get that the absolute value is equal to the absolute value because d could be even. So that means that the left side without the absolute value is equal to the right side without the absolute value, or the negative of the right side without the absolute value. And we're going to show that it is the former by going through each real case. So let's go ahead and do that. If a and b are positive and all the expressions are real, then that expression is positive, and so that expression is positive. That expression and that expression are positive, and so that expression is positive. And so as we already know that they're equal with the absolute values, we also know that they're equal without the absolute values because both the left and right hand side are positive. If c is even and all expressions are real, then that expression is positive, and so those two expressions are positive, and so that expression is positive. And so as we already know that they're equal with the absolute values, we can now know that they're equal without the absolute values. If a is positive, b is negative, c is odd, and all expressions are real, a over b is negative, and so that expression is negative. That expression is positive, and that expression is negative, and so that expression is negative. Positive over negative is negative. And so as we know that they're equal with the absolute values, we can now know that they're equal without the absolute values because we have both the left and right hand side to be negative. If a is negative, b is positive, c is odd, and all expressions are real, then that expression is negative, and so that expression is negative. That expression is negative, that expression is positive, so that expression is negative, and so the property holds true. If a and b are negative, c is odd, and all expressions are real, then that expression is positive, and so that expression is positive. that expression is negative, that expression is negative, so that expression is positive, and so the property holds true. If a is 0 and all expressions are real, then a over b is equal to 0, and so that expression is 0. That expression is 0, and so that expression is 0. And so as you already know that 0 is equal to 0, we can now know that that expression is equal to that expression. Now, however, we cannot have b to be 0 because then we have undefined expressions. What happens when you have irrational exponents? If you punch that into your calculator, you get this. Now 2 cubed over 5 cubed is equal to this. As we get closer and closer and closer to 2 to the pi over 5 to the pi, the right-hand side becomes closer and closer and closer to 0.05621. And so it would make sense for 2 to the pi over 5 to the pi to be equal to 2/5 and that to the pi. Thank you for watching this video. Here is the link for the playlist about the why behind for some properties of exponents.